of PDs that they're going to have multiple solutions unless we have some boundary or initial conditions. Okay. And this really gets into some of the main questions of the course. Okay. So what are the main questions of this course? Okay. First of all, we are going to look into what's called the well-posedness of PDs, okay? Why does this matter, okay? And what does well-posedness mean? Well-posedness really has three main components, okay? One of those is existence of solutions, okay? You may have some physical, biological system that you're modeling. You write down some PDE in order to model it, but do you even know that the model that you've written down has solutions? You could try numerically simulating it, but we know that in a lot of instances, numerical simulations of PDs don't always replicate what the true continuous system would do. And so thinking about methods to just identify if I have a solution to the mathematical model that I've written down that's a PDE is broadly helpful in applied mathematics, okay? Another aspect of well-posedness is uniqueness of solutions, okay?
So,
and you go ahead.
Which one is preferable, analytical solution or a numerical solution for a PDE?
So if you can get an explicit solution, that's great, okay? But the question is, how much trouble do you want to go to in order to get that, or to discover that you just can't find an explicit solution? So it's a real balancing act for, PDEs that people have studied a lot. Typically, you can obtain an analytical solution, and that's helpful to have. For a very complicated model that is far from anything that anybody else has an analytical solution for, a lot of times it's most helpful to just numerically simulate first and find what happens. So the types of methods that we're talking about really apply to models that have some, link back to PDEs that people know that you can solve in the first place. Okay, but there is a lot of ongoing research into using analytical solutions that people have already to sort of build approximate solutions. And if you take the asymptotics course next semester, that's what we'll talk about. That's a good question though. So yeah, if you can get an explicit solution, that's great. It's just sometimes it's very hard to do, okay? Solution uniqueness really speaks to, whether the solution that I have is the only one that there is. And if I was to, numerically simulate this PDE and I found something else, if I might think that something's wrong with my simulation, or just that maybe there's multiple solutions to this PDE. And then the third aspect is stability, or sometimes this is called continuous dependence, with respect to the initial and boundary data or conditions, okay? So continuous dependence, okay? Why is this important? Well, because almost any model that you write down in applied math, if you have some initial parameters for that model or initial data for that model, there's always going to be some uncertainty associated with that. And so you can never be sure that the initial condition that you write down to model some system is going to precisely correspond to whatever you're trying to model. And so if your PDE is very, very sensitive to changes in initial data, you need to know that in order to kind of account for any problems or sort of misleading conclusions that you might get by thinking that, well, if I just change the data a little bit, my solution's going to still look the same. Okay. Other aspects that we'll talk about are what's called regularity, okay, or basically how smooth is the solution, okay? And we'll come across this when we start talking about waves and shocks. So one of the earliest models of traffic jams was a traveling wave and a PDE that generated shocks where you have a discontinuity basically in the solution. It's fine if you have an irregular solution, maybe it's not necessarily smooth, but you need tools in order to deal with that and you want to know if that's happening, okay? Another thing we'll talk about is the classification of different types of PDEs, okay? So what order is a PD? So the transport equation, the first one I wrote down is a first order, but the wave equation that we wrote down second is a second order PDE. And we're going to really deal with different kinds of second order PDEs in this class. That's going to be the bulk, kind of the body of this class. And I think most of you have had the prerequisite PDE class. You would have seen elliptic, hyperbolic, and parabolic PDEs before. And these are the different sort of canonical models that you typically look at in a PDE course. They're called Laplace's equation, Poisson's equation, the heat equation, and the wave equation are each kind of the canonical PDEs of these three different types. And we'll get more into how we classify those a little bit later. We're going to talk a lot about linear PDEs, but we'll also talk about nonlinear PDEs fairly early. In particular, method of characteristics can be used to analyze nonlinear PDEs, but of course, linear PDEs, you would imagine, are easier to get solutions for a lot of reasons. And then also homogeneous and inhomogeneous PDEs, okay, ones that only involve the unknown function, u, for example, in the case of the example that we looked at, or inhomogeneous where you have some forcing function. And physically, you often think about this as, you know, injecting additional energy into the system, okay? So the other thing that's important when we're writing down PDEs, and we'll see this early on when we start talking about the transport equation, is what are acceptable initial and boundary conditions, okay? Again, when you're writing down a model, you have to think about, well, did the model I just write down have a solution? One way that you may prevent it from having a solution is that if you create boundary and initial conditions that disagree, okay? If this boundary condition generates dynamics that are in discord or in disagreement with the boundaries, then you have to sort of fix that. So there are ways of sort of checking that. And so typically we think of how to set our boundary conditions and initial conditions with respect to well-posedness. How many boundary conditions can we have? Okay. In the case of the order of the PDE, the order of the PDE is going to give you some clue as to how many boundary conditions you can have and on what domain you can put them. We'll also talk about both explicit and implicit solutions, okay, where I have an honest to goodness function that is the solution of my PDE, or maybe I just have an expression for the solution of the PDE in terms of itself. And I will tell you that an implicit solution is still better than no solution at all. Okay. As you might gather, I also like connections to physics, chemistry, biology, okay, some imaging and engineering, okay? And I think that having a physical model of the phenomenon that the PDE is modeling in mind can help not only understand the equation itself, but also provide some guesses as to types of the solutions that you would see from those PDEs. And so having all those tools available is extremely useful for understanding how PDEs and their solutions fit together, okay? And unlike maybe more of a analysis-based PDE course or a purely analysis-based PDE course, we're interested in finding solutions and understanding properties of solutions. So you can take some PDE courses, honestly, where people will just prove existence and uniqueness and you know, continuous dependence all day long, right? So, and there is great value in this, but for applications, I think getting a solution or finding all of the ways that there are for finding solutions is really the type of toolbox that we want to have in hand. And the issue with PDEs is that there's no method that will solve all PDEs. We have to generate a set of, you know, 10 or 20 different ways that we might solve a PDE, and then know how to deploy these strategies depending on the one that we encounter. Okay. We'll also talk some about what are called classical versus weak solutions. Okay, this has some to do with the regularity of those solutions with respect to how many times they're differentiating. A lot of times you're going to have a solution to like a second order PDE, but it's not actually twice differentiable. And so you need to sort of reframe what you think of as a solution in terms of weak solutions. And then there's also what are called sort of special solutions, which show up sometimes when you have, you know, multiple solutions or sort of special cases of PDEs. Okay.